Wow. Listen, you guys, I've been over here talking and just installed keycord on... Oh, that was a big mistake of my own. Oh, I definitely want that to be... definitely want to capture that. So yeah, I've been streaming for the... or I've been recording and talking for the last 12 minutes, and it was not streaming at all. So I totally apologize for that. Yeah, it's not going to change the... schedule. I'm still gonna go for about an hour, but yeah, my apologies. So yeah, let's continue and pick up where we were with the constant numeric types. When you write down a constant number like 1, 2, 3, 4, it has a type, but what type is it? Let's look at how C decides what type of constant it is and how to force it to use a specific type. But first, let's go to YouTube and let's check on Keenan Can Do. Who is us, right? We are Keenan Can Do. I am Keenan Can Do. You guys aren't Keenan Can Do. You guys are whoever you are. So Keenan Can Do here is now live, and we have 96 subscribers. 96. So we're only 4 away from that 100. Let's continue to push that. Share it with your friends. Whoever likes things like this, whoever likes working with Emacs, whoever likes actually coding. In the beginning, at least for now, we're going to be less AI. I still think there's something to be said about doing it by hand. In my day-to-day as an engineer, I do use AI in some stuff to help with some things, but that's all I have to say about that for right now. So again, let's push for that 100 subscribers and show everyone that you love this stream, because if you love the stream and they love you, they're probably going to like it as well. Okay, that's my spiel. Let's go back to hexadecimal and octal. In addition to good old decimal like grandma used to bake, CL supports constants of different bases. If you lead a number with a 0x, it is read as a hex number. Int A 0x12A2B hexadecimal, int B 0x1A2B. Case doesn't matter for hex digits. That makes sense because why would it? It's a numerical thing. Print F, X is a hexadecimal specifier. Is it? Well, let's just go ahead and check that. We can, the good thing about C in the documentation is everything is well documented, so we can just do man print f.3, man, not main, man print f.3, and we'll see the specifiers, and they're saying that X is the specifier for let's do it like that. Maybe we'll find it that way. There we go. The value should be 0 padded in conversion. Okay. Let's see what X is. X. The unsigned int argument is converted to unsigned octal O and unsigned decimal U, or unsigned decimal X in X notation. Yeah, so right there. Self-documented in Linux. We just go to our documentation. We look up printf, the man pages for printf, and we find where the X is there, and we're good to go. Now, the cool thing about the prelude with Emacs is you could also essentially do the same thing. If we go look at our prelude documentation again, we'll see that we do have the documentation key binding for searching DuckDuckGo. I believe it's right here. Yes, it is. It's Control C and then capital U. So if I'm in there, I'm reading about this. We were reading it. We saw that he said the X here. That's kind of cool. We could go Control C, capital U. What is the URL? The URL? No, I didn't want a URL. I wanted to go to DuckDuckGo. Let's go back to our documentation. Control C, capital U. Search in DuckDuckGo for the thing under point or an interactive query. And so the query is going to be printf, man printf, right? Printf X specifier, right? Bad URL. So that's not actually the search we wanted. We wanted to search. So let's go back to Control C. And what did capital U actually give us? It's view URL, but we wanted capital U. So if I type capital U, that still says URL. So something's not right. So let's go into MX and see what is DuckDuckGo, which is crux search DuckDuckGo search duck. No, if I just type duck, it's prelude duck duck go. It's Control C, Control / and then D. So it's Control C, Control / and then we see duck duck go there. So I'm not sure why it has it in there. I think because this prelude mode and C, the key bindings for C get overridden in it. So in any case, we'll do our duck duck go. We'll say we're still looking for printf x specifier, and then the x specifier in the printf is just print an integer in hexadecimal format. There we go. Yes, it is. See, there we go. So the DuckDuckGo search assist helped us pretty quickly. So you could easily use that, or I would get into the habit in case like the internet went down on you or whatnot. Then, like I said, you have the self-documentation right here. C is self-documenting on Linux systems because everything is included in the documents. We could even, I think, do we have info? Do we have info? We do have info. So we could say info printf, and we would get the info documentation for printf, and that would be for info. I'm not as good with info. Maybe on a future stream, if you want to do that, we could go over learning info together. So I digress, and you want to send me back. Let's send me back to the lecture at hand. If you lead a number with 0, it is read as an octal number. Int A012 print an octal number. This is particularly problematic for beginning programs who try to pad decimal numbers on the left with the 0 to line things up nicely and pretty, inadvertently changing the base of the number. Okay, int x111 is decimal, int y00 is decimal 73, int x is decimal 585 because it turns into octal. A note on binary. An unofficial extension in many C compilers allows you to represent a binary number with a 0b prefix. Binary prints 42 decimal. There's no printf format specifier for printing a binary number. You have to do it a character at a time with bitwise operators. Integer constants. You can force a constant integer to be a certain type by appending a suffix to it that indicates the type. We'll do some assignments to a demo, but most often devs leave off the suffixes unless needed to be precise. The compiler is pretty good at making sure the types are compatible. Makes sense. The suffix can be uppercase, lowercase, and the U and L can appear either one first. So that's like in Java, you put a D to make something like a double or something, or put a F to make something like a float. Kind of similar situation, I believe. Not needed, not wanted, not something we are going to do. Okay. I mentioned in the table that no suffix means int, but it's actually more complex than that. So what happens when you have an unsuffixed number like int x1234? Excuse me. What type is it? What C will generally do is choose the smallest type from int up that can hold the value. But specifically, that depends on the number, space, decimal, hex, or octal as well. The spec has a great table indicating which type gets used for what unsuffixed value. In fact, I'm just going to copy it wholesale right here. So reads the type of an integer constant is the first of the corresponding list in which its value can be representative, and then goes on to show this table. None, int, long int, u. Whoa, that table does not seem very easy to understand. The table doesn't add any visibility or any understanding. It didn't help me. Let's see what the table does. What's that saying is that? What that's saying is that, for example, if you specify a number like 1, 2, 3, 4, 5, 6, 7, 8, 9, u, first C will see if it can be unsigned int. If it doesn't fit there, it'll try unsigned long int, and then unsigned long int. It'll use the smallest type that can hold the number. Okay. But if you didn't put a U there, does it also do this? Yeah, because int. Okay, so if there's no int, it goes to int, tries the int, and then it tries to go downwards. Okay. Floating point constants. You'd think that a floating point constant like 1.23 would have a default value of float, right? Surprise! Turns out unsuffixed floating point numbers are type double. Happy belated birthday. You can force it to be of type float by appending an F or F, its case incentive. You can force it to be of type long double by appending L or L. For example, float x 3.14f, double x 3.14, long double x equals 3.14L. This whole time, though, we've just been doing this, right? Float x equals 3.14. Isn't the left a float and the right a double? Yes, but C is pretty good with automatic numeric conversion, so it's more common to have an unsuffixed floating point constant than not. More on that later. Scientific notation. Remember earlier when we talked about how a floating point number can be represented by a significand base and exponent? Well, there's a common way of writing such a number shown here, followed by its more recognizable equivalent, which is what you get when you actually run the math. Writing numbers in the form a times base b to the e is called scientific notation. In C, these are written using e notation, so these are equivalent. You can print a number in this notation with the specifier e. Again, we see a specifier, we just want to get in the habit of just looking at the documentation, just getting used to looking at the documentation, searching things for the documentation. So we're saying that e, so we're looking for comma e. Where's e? Comma e. There it is. Okay, wait, that's not the first time we see it. There we go. E. The double argument is rounded and converted in the style where there is one digits, which is non-zero, in the argument before the decimal. Yeah, so the scientific notation. Okay. You can print a number in this notation with %e. Prints 1, 2, 3 plus 5 to the 0. Couple little fun facts about scientific notation. You don't have to write them with a single leading digit before the decimal point. Any number of numbers can go in front. Double x equals 1, 2, 3. Okay. However, when you print it, it will change the exponent so there is only one digit in front of the decimal point. The plus can be left off the exponent as its default, but this is uncommon in practice from what I've seen. 1.2.345 e to the 10 is equal to 1.2345 e plus 10. Yeah, if you apply the F or L for e notation constants, you can apply the F or L suffixes to e notation constants. Hexadecimal floating point constants. But wait, there's more floating point to be done. Turns out there are hexadecimal floating point constants as well. These work similar to decimal floating point numbers, but they begin with a 0x just like integer numbers. The catch is that you must specify an exponent, and this exponent produces a power of 2, that is 2 to the x. And then you use a p instead of an e when writing the number. So 0xa.1p3 is 10-0625 times 2 to the 3 equals 80.5. When using floating point hex constants, we can print hex scientific notation with a %a. Is that so? Is that so? We're going to say it's so because it seems to be so. Okay. So what's the next chapter? The next chapter is after chapter 14. What comes after 14, folks? 15. Conversions. This should be interesting. So it looks like there's 1, 2, 3, 4, 5 sections in there. So let's quickly scan the sections. So this is kind of like how to read something new. You want to scan the sections first to get an idea of what you're going to be covering. And then you can go deeper into them after that. So we have string conversions. Looks like converting string stuff. Char conversions, that would make sense. That's actually, that I do want to do because that's what I was trying to do with my previous little program to read in a char value. So I want to do that again. Numeric conversions. Implicit conversions. Explicit conversions. Okay. Well, let's start. We might get through this chapter tonight. We might not. We're getting close to the chapter that I wanted to be to, which would have been multi-file projects. Wait, where's the preprocessor? When do we get the preprocessor? Oh, that's chapter 19. But we're not really going to need the preprocessor stuff until we'll be able to make some cool stuff, I believe, before around 17. Maybe even convert, maybe even today after the conversion. So let's jump into that. So in this chapter, we want to talk about converting from one type to another. So let's just, I just want to start with a new folder here. So we'll call it conversions. And we'll go into it, and let's do a main.c there. Okay, we know we're going to always need this because we want to output stuff, right? And we're going to have this, and we're going to return 0, right? Yes, that's right, Keenan. Thank you, guys. Thank you. Thank you for thank you for telling me that's right. And then what is n? Is n the thing that cleans the buffer up? Yeah, I like that. Okay. So let's do a printf just to make sure we're all set and ready to go. Look what I didn't forget there. I did not forget the new line. I haven't been forgetting it lately. And then let's also make a makefile. Make a makefile. Our C flags are going to be the same what they always are, which is give me the warnings all, give me the warnings extra, be pedantic, 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 and give me standard equals C89, and output some G flags, and we're gonna go O because we want to output object. So our main object depends on main.c, right? And it's simply going to be calling GCC with the C flags, right? The C flags. If I can spell C flags, then I can spell it, but I can't spell it. Main.c, right? That should give us a compiled object, but I'm not sure because sometimes I make mistakes. Oh, look at that. I didn't make a mistake. No mistake making today, folks. We are over here not making mistakes. So let's go then into the source learning. Oh, C learning. And then what did we call it? We called it conversions. Boom, we're there. Let's do main. Hello world. Yeah. Can your Vim do that? I borrowed that from Soding's channel. But yeah, so that's a cool little workflow. All right, so let's go back and let's just add in a phony clean target. We're just adding a clean target, and it depends on nothing, and it just does the well, I guess it does depend on main, right? And it does the RM of main dot C. No, not C. Main dot main. Is it just main dot O? Boom, 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 boom. What is there? It's just main, yeah. RM main. That's it. So now I should go back, and then I can do make clean, compile, make clean, boom, and now we just have just the C file. Okay, so we're ready to begin. Okay, string conversions. Before we talk about conversion happen, let's talk about how they work when they do happen. String conversions. Unlike many languages, C doesn't do string to number and vice versa conversions in quite as streamlined a manner as it does numeric conversions. For these, we'll have to call functions to do the dirty work. Numeric value to string. When we want to convert a number to a string, we can use either sprintf, pronounced sprintf, or snprintf, pronounced snprintf. Well, isn't that just genius? These basically work like printf, except they output to a string instead, and you can print that string later or whatever. For example, turning part of the value pi into a string. Oh, sounds like the laundry machine is going over there, folks. And the door's closed. Okay, we're good to go. All right, so let us try this out then. So we're going to say, give us a char array with 10 items. Give us a float f of 3.14159. What is that number? That is pi. You're correct. That is pi. And then we have sn print f s 10. I guess that's the size. And then we want a specifier. So we're printing a float out. Convert f to string, storing an s. Okay. And then we're going to print it afterwards. Print f. String value. Give us a string. Give us a new line because we always forget that. S. Okay. Okay. Well, let's compile this first to make sure it compiles. Bum, 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 bum. Do I not have it? Why didn't... What? sprint. I do have standard input. Include standard input io.h. So how come it's not? That's an interesting warning. Let's see if it works though, because that's an interesting warning. String value, yeah. Implicit regression function. Is that function not in there? Is defined in header. This is probably fixable by adding include. I already have include. What if we recompile? Oh, then it worked. That was interesting. Okay, so let's talk about it. So on line 6, we are getting a we're setting up a array of 10 chars. Couldn't I have just, let's see. Couldn't I have just let's see, couldn't I have just said pointer char pointer like that, and then I would have to allocate for 10. Trying to learn how to do this with all the different stuff that we've learned. Okay, so we have P here. I know that P is not gonna work because I didn't allocate it, right? Yeah. S, where's S? Oh, oops. So recompile again. Okay, so the warnings now are why is it doing that? And then it works. That's weird. That is weird. Oh, segmentation fault. Yes, because it's not my memory. So I would have to ask for memory because see if I can remember the malloc. Well, you know what? Let me just go to the man malloc. Man, not main. Size and T. Okay. Okay. So I essentially could just say function allocates or returns a pointer. The memory is not initialized. If size is 0, then malloc returns a unique pointer value that can later be void pointer. Size of t. And it's going to be, we want a char pointer. Okay. And then we want to say p equals malloc size of char times 10 items, right? And malloc is needed from standard lib. Standard lib, yeah. Okay, we're getting there. We're getting there. I am getting there. I'm not sure if you're getting there, but I think we're getting there. Okay, P. So I think this would work now. Look at that. It did it again. I don't... And then it worked that time. Oh, but I didn't... okay, I'm still going to try it, but I didn't add... I know what I didn't do is I didn't add... Yes! Ah! So I did manual memory allocation and did it. Well... I didn't free the memory, so let's go ahead and free the memory. So we'll free P now. But yes, and then recompile, and I'll get the errors, and then recompile again. I don't know if that's a bug with Prelude or what's going on. But let's go ahead and take a snippet of that because that was cool. That's my first time that I kind of, because we did the memory allocation yesterday, but we didn't go back and look at the documentation. So it's kind of I'm starting to grok it. I'm starting to understand, you know. That's kind of cool. But wait, what was the value? Value 3.1490. 1459. Yes, because there's junk in there, right? Because whatever the memory was beforehand. So that's cool. So let's say we actually wanted the memory size to be 25 items, right? In our recompile. I don't know what... I don't know why it's doing that. That is so weird. And then I'll run main. Why didn't we get the junk? Oh, because of the size. We only said we wanted 10 of the items, so... Let's say... maybe down here I have to say... 20 items, or 25, whatever the size is, right? Then recompile. I'm just not gonna... I'm not gonna keep on I don't know why. Is it something in my make file? Let's look in just a minute. I don't know why it's doing that. And there was no junk. How come there was no junk? .1459. It's still giving me a junk 0. You know why? I think because there's probably some null terminators there. In a null terminator outputs your a null terminator outputs your value, right? So if instead if we do it like this, so instead of doing it like this, we could go let's give us an int I, and we could say while I equals 0, I is less than let's just do the first 15 because I want to see what the values are going to be. And then we could say printf percent char. We don't want to print the new line until the end, right? And we want the value that's at P, right? And then we want to move P plus plus. And when we are done, we want to print a new line at that point. Okay? Does that sound so? So then we're gonna see every char that's printed, and I'm assuming we're probably gonna have a null byte in there because it's like junk memory. We don't know what the memory was at that time when we grabbed it. So let's recompile. This time I get an error. I thought you could do in a while. Is it with just the commas then? Yes, it's just with the commas. Okay. It's with the comma. Okay. So let's go ahead and run that. Whoa. Whoa, whoa, whoa. While I float. Oh, what? So I'm going to the next char. Like, what if I comment out this completely here? I don't know why the compiling is always doing that. I really don't. I just don't. Segmentation. Why did we get a segmentation dump this time? Okay. Give me a pointer. Oh, because I don't need... It's just the p-value there. Right? Wait. Format expects argument type input. Argument 2 is type char. Okay. Definitely broke something there. Why? Oh. You know what? I never am iterating. I didn't ever iterate I. That's what it was. So I iterated. Yeah, that's my fault. I never iterated I. We did iterate P. Okay. So this should give us the back. And then now we should be able to see segmentation fault still. Why would a segmentation fault happen? Printf the character at P, then move the pointer for P forward, and then move I, or increment I. And that's my memory, so why can't I do that? Size of char times 25. So you give me whatever 25 times the char value is. Okay. String value %s. Come on, Keenan, what are you missing here, buddy? ISO 90 forbids mixed declarations in code. Yeah. Where do I have decoration at? Float. Warning. Where did I have declaration in code? Declaration after the statement. Where's the declaration after the statement? Let's remove this for now. Oops. Okay. And let's go back here. And okay, recompile so we can start off a good spot. Well, where am I mixing the declaration? Float? Is it because this malloc char has to? Whoa. I don't know what that was. Should this be down there? Is that what they're saying? Yeah. Okay. Okay, so I got the malloc the size of. But why am I not able just to look into the memory? It's my memory. You gave it to me. So if I didn't want to do this, P, so I could just print FP. Okay, let me just, whoops. Let's just print the value. Oops. Of P there. It was an int. Yeah, you could give me, okay, so you could give me the address of P. Right? This is the address of P. Then I'd be able to see the address of P. Okay, so that's the address of P. Weird address. Wish it was hexadecimal. Okay, and then I could P plus plus, and then I want to print the address of P again. Aborted free invalid pointer. I'm not moving my pointers correctly, I don't think. That's what it is. Okay. This when's the fun stuff? Is it the hard stuff? Okay. So why did it give me... So I have a pointer, a char pointer. You give me a piece of memory. Oh, wait. Okay, so that's the memory. And I want it in hexadecimal, so let's change that. X, recompile. Okay, so there's the hexadecimal value of the memory, but it didn't move the memory. Why didn't it move the memory? I'm gonna figure this out. Let me go 5 more minutes. Format X expects unsigned but argument has type char star star. Char star star. The address P. Okay. It's a pointer to the memory. Okay, so you gave me a pointer, you gave me some memory. And the size of it is should be 1. Size of pointer. LU P. Size of P. LU. Okay. Try to run it again. 8. So my pointer is 8 bytes. Y go to man point malloc. Allocate size bytes and returns a pointer to the allocated memory. The memory is not initialized. Okay, so size of char bytes. So char is 1 byte. So that should be 25 bytes. Right? So I should be able to iterate. What am I... I'm gonna get this. What am I doing wrong here? Okay. So I print F. First memory location value, and that would be, I want a char. A char. Right, and in order to get that, do I have to cast a char to star P? Oh, I see. I think I'm not supposed to be changing the pointer, but I can move the pointer. Just remembered that. There's nothing there. There's no value. There's no value. Okay. Okay, so for int I equals 0, I is less than, let's say, 20, I plus plus, right? What we're going to do is we are going to get the times I times I, right? And then we're just, let's if it out actually. We'll if it out. If. That's gonna be a D. Oops. Okay. Oh. Oops. There we go. Main. There's no value there. Now we'll do that reassigning thing, sn print f of s10, and it's a float that we're putting in, converting to the string. we have the memory. Storing in S. Writing at most 10 characters, including the null terminator. Oh, it's so we do have the null terminator. Okay, so we are going to see the null terminator, and we want to store this in P. Okay, so let's recompile. Recompile again, because I don't know why it's doing that. Main. There we go. Now we get to see all of our junk memory. Oh, that's kind of cool. 3 point... But why... Memory location value. Shouldn't it be... Shouldn't it be... Let's try D's. Okay. So why didn't the char work? Okay, so malloc size char 25. So we've stored the string value because those are chars in there. So yeah, char ith memory location char plus p times I. Is that right? I don't know if I need to cast it. Okay, so it's gonna be no, because you're at, okay. So we need to take I times I. We need to take something times I. We know that. What is that thing times I? It's plus. So the first one is obviously gonna be 0. We want to plus nothing. Plus. Hold on. Let's figure this out. Okay. Come on, Keenan. This would give us the thing pointed to. That would give us the first. So if I did that, that's just going to give us... Let's just test it. I think that's just going to give us the same thing a bunch of times. Yeah, 51. Okay. So now I need to say... plus 0, because 0 times anything... P plus P times 0. Come on, why am I having a brain fart? Do I need to, maybe if I write it down. We're looking at the memory. Let's just do this. looking at 0th, 1th, 2th, 4th, okay. And here is the first value. That's where the pointer is at. So we want to stay there. Times 1 times, okay, 0. Okay. Plus, so it's plus 1 times I. Okay, so that's just plussing it, but we need to it's going to be P oops, what? P times I. P plus 1 times I. Well, this time we got an error. Oh, there we go. Oh, another one, okay. Ah, there we go. Okay. So those are the char values. Or those are the decimal values. So now if we do the char. There it is, 3.14. Cool. And then I don't know what the junk memory in there. It looks like there was no junk memory. But yeah, that's iterating through it using the memory. There was no junk because it did the null terminator. But if we put in here 14 or 20 items, let's do 15. Now it's gonna write all of this stuff. It didn't write no junk. Oh yeah, well there's one junk. So there's one junk value of that 0 that's showing up there, I guess, for some reason. I don't know. Unless that's the null terminated value, which we don't actually see the explicitly null terminated value in the output. So that's interesting. Don't know why, but okay. So that's cool. So that's cool. So I kind of figured out that little issue there. So the pointer is P plus 1 times I, which would give us the first, because 1 times 1 obviously is identity, 1 times 0 is 0, then 1 times 2 is everything. So it's just moving the pointer, moving across the pointer into the memory location. So that was fun, but what that didn't tell me is why am I not seeing a lot of junk in that memory? Could I look at the hexadecimal value of that memory? It's all 0. So it is kind of cleared out. It does kind of clear it out. I thought it didn't clear it out. Because it says malloc. Right? Doesn't it say man malloc allocates returns? The memory is not initialized. But it is initialized. So if we go back here, Control C, Control that, and then D. Malloc says not initialized, but it's all hex 0. Oh, why'd it go to that? Sorry, I went to a different one. I went to this one. Yeah, here we go. Dynamic is cornerstone. Blah blah blah. Blog reducify one malloc. Sometimes reserved. Explore the row. What are malloc? And yeah, malloc is uninitialized. This means the contents are indeterminate. May contain garbage. Calloc allocates memory. The common misconception: malloc returns uninitialized. Many developers learn that malloc returns, which they interpret as filled with random. While this is often true, it's not universally the case. In practice, malloc may return memory that appears zeroed, leading to confusion. Consider this example. Yeah. On many systems, the large allocation will point 0, while the small allocation may print a non-zero value. Why? The answer lies in how the OS and C standard allocate memory. Malloc failed. Return. Why does malloc sometimes return zeroed memory? The key inside is that malloc itself does not, but the operating system often does. Okay. So the operating system is sometimes returning the zeroed memory. Okay. So that makes sense. That's totally understandable. Makes sense to me. Okay, so we've gone about a little over an hour today, including the mishap that I had with the information with the stream. So we're gonna go ahead and call it an evening. Thank you guys for joining me, learning about we didn't get too far into 15, but then we played around with some malloc. I did my actual first manual memory allocation and then played out with some errors on that. We did some prelude stuff. If you like what you see, hit that like button, subscribe, tell others about our streams, and come and join us as we learn some low-level program. I'll talk to you guys tomorrow night. Bye, everybody. Have a good evening.